Okay, this video is about oxidizing and reducing agents. It's not going to be that long because it's not a very long topic. A reducing agent is a substance that has the potential to reduce another substance. This is going to be anything that is oxidized is a reducing agent, because in a redox reaction, you have one thing oxidized and one thing reduced. So if this is oxidized, it means that this has reduced the other one. That's why it's called the reducing agent. So you just remember, when you identify what is oxidized and what is reduced, then the agent part of that is the opposite. What is oxidized is the reducing agent because it causes something else to be reduced. And in the same vein, my cord here, I'm trying to keep the microphone close to my mouth. In the same vein, an oxidizing agent is a substance that has the potential to cause another substance to be oxidized. So this is going to gain electrons, aka be reduced. The substance that is reduced is the oxidizing agent. The next part of this is basically just applying what we learned in grade 10 about the activity series in respect, or with respect to redox reactions. So if you remember this activity series, you've basically got the group 1 and group 2 metals that are at the top, and then you've got some transition metals, and then the precious metals are down there at the bottom. And this can be an indication of the strength of oxidizing and reducing agents. But honestly, I don't want to spend too much time on it because I think that you can figure it out based on what you already know about the tendency of specific elements in the periodic table, whether they tend to gain electrons or lose electrons. So if you just think about the metals at the top, let me get my little laser pointer. All of these metals at the top are active metals. So they're going to be very eager to get rid of electrons to have a stable electron configuration. When you get rid of electrons, that means you are being oxidized. So these guys up here are very good reducing agents. Okay, so if you put together the knowledge that I've taught you in the past and you just put it in a new context of like reducing and oxidizing agents, you already understand, according to the periodic table, that the active metals in groups 1 and 2 are called active metals because they lose electrons. And now you can put that in the context of oxidation. So the active metals are easily oxidized, which means they are strong reducing agents. On the flip side, let me get to here. On the flip side, excuse me, you have the nonmetals on the right-hand side of the periodic table, specifically group 7 or 17, like 16, 17 in that area. They really want to gain electrons to have a stable electron configuration, as you were taught in grade 10, just in case y'all forgot. So these are going to be very easily reduced, which means they are strong oxidizing agents. So you can see this is the table that is in your book. It's really easy to figure it out because you've got reducing agents here, and all of the strong reducing agents are the active metals, because these are the guys that are going to be oxidized. They want to be oxidized because it gives them the stable electron configuration. And on the flip side, you've got oxidizing agents, and we're increasing strength going down. We look at the ones at the bottom. These are going to be the ones that are more likely to be reduced, and therefore they are the oxidizing agents. Okay, that's that. And then the only, oh, hello, we're frozen. The hell. Okay, so in a different context, my iPad is frozen. Okay, whatever. In a different context, you can use the activity series and the strength of oxidizing and reducing agents to figure out that if you put, for example, a zinc metal in a solution of copper, you can predict what's going to happen based on their tendency to be oxidized or reduced. So you have, okay, the screen on my iPad does not match the one that's on my screen because it's being weird. Does that work? Okay, this still works. So I'm gonna have to go in blind. All right, so we've got zinc and copper. Let me just use this then. Where am I? Am I getting close? There we go. Zinc I'm trying to do this on my iPad, but using my screen as a guide for where my pen is. So, oh, we can see zinc and copper. All right, there we go. Circle those two. Okay, very strange. Zinc is above copper, so it is a more active reducing agent because our strength of reducing agents is here. Oh God, that's horrible. Here at the top, I'm telling my iPad screen is just black. You see, it's so weird. Look, that's what I see in my screen. Oh, there it goes. Finally, maybe I just needed to like pick it up and show it some love, and then it's like, okay. Anyway, I hate online teaching. Have I mentioned that? Okay. Anywho, so zinc is above copper, which means it is a stronger reducing agent, which means that is going to displace copper ions from solution of copper compounds. And so copper, the copper ion, is a more active oxidizing agent than zinc. And so then you can kind of just predict what will happen if you put two of these metals together based on their strength of oxidation and reducing. And okay, same thing for nonmetals. Oh, it went black again. All right, whatever. The last thing is disproportionation. Fancy word for basically saying that one substance is both oxidized and reduced at the same time. And a really good example of this, just to skip all of that crap, is hydrogen peroxide, because the peroxide ion, I guess I can go back here. The peroxide ion is O2 minus 2. That makes each oxygen atom have an oxidation number of minus 1. And so then you can put it in an equation. This is when hydrogen peroxide decomposes to form water and oxygen gas. You can see that hydrogen peroxide in this example is both oxidized and reduced. The oxygen atoms that become part of gaseous oxygen molecules are oxidized from -1 to 0, and the oxygen atoms that become part of water are reduced from -1 to -2. So one substance is both oxidized and reduced. It is possible. So disproportionation is a process where a substance oxidizes itself and reduces itself. So it's self-oxidizing and self-reducing. Why should we give a crap? Well, something very interesting happens when you put this process in nature. There is something called a bombardier beetle. A bombardier beetle defends itself by spraying its enemies with an unpleasant, hot chemical mixture. This process is catalyzed disproportionation of hydrogen peroxide, and it produces hot oxygen gas. And that production of hot oxygen gas gives the insect the ability to eject the irritating chemical from its abdomen. So we're going to go ahead and look at this in process. So this is why we care about disproportionation. That's the bombardier beetle. So it's a boiling caustic liquid that gets sprayed out of its abdomen, and this is catalyzed by that disproportionation of hydrogen peroxide. Hydrogen peroxide, of course, is caustic, which means it's alkaline. And it very nearly cooks itself in this process, but it is a really good defense mechanism, as you can see. Ta-da!